Hi, I'm Hiroki Yoshikawa from Osaka University in Japan. In this presentation, I would like to talk about our work. The title is Data Balancing for Thermal Comfort Datasets using Conditional Wasserstein GAN with a Weighted Loss Function. Researchers have worked on thermal comfort estimation as a classification task using machine learning. This is 7-point scale thermal comfort, which is generally used as classes to estimate in such work. Thermal comfort datasets are usually imbalanced because extreme feelings are rarely reported in such an actual environment. Imbalanced datasets lead to biased estimation, which is not helpful for users in environments that rarely appear. Data balancing is one of the preprocessing methods dealing with imbalanced dataset. Data augmentation is one of the solutions which generate layer samples based on original trend. As illustrated in this figure, thermal comfort dataset is usually imbalanced, such that extreme response is rarely reported. To moderate the imbalance of the dataset, data balancing is conducted. In the data balancing method, we augment such extreme response to balance the number of samples in each class. After the data balancing, the estimator can give fair judge to us. Synthetic minority oversampling technique, which is called SMART-based methods, are predominant data augmentation. This method is based on the simple idea of the interpolation between two samples. Recently, GAN-based data augmentations attract researchers because of their high performance. GAN is a generative model which can generate samples by learning the trend of training data. For thermal comfort dataset, comfortGAN was proposed as a state-of-the-art data augmentation method. This is an overview of our work. We propose a derivative of comfortGAN which prevents biased data generation. Imbalance of thermal comfort dataset probably causes biased data generation by GANs. To prevent the biased data generation, we introduce weighted loss function when we train comfortGAN. We train the generative model using imbalanced dataset with a weighted loss function. As a result, it can generate samples using this balanced generative model. comfortGANs constructed by conditional Wasserstein GAN with gradient penalty called CWGAN GP. Conditional GAN can generate a sample with a label. Double GAN GP improves training stability compared with GANs. Loss function of generator and discriminator of comfortGAN are calculated from this formula. This is the discriminator's output to generated samples, and this is the discriminator's output to original samples. This is the gradient penalty. It helps to prevent gradient explosion and vanishing. For the fair training of comfortGAN, we introduce weighted strategy into them to moderate imbalance among classes. Our weighted loss function is based on inverse ratio of the number of samples in each class. We divide the number of all samples in the training data by the number of samples in the class where the sample belongs. In this method, a rarer sample has heavier weight. These formulas are loss function of generator and discriminator in our method. We multiply discriminator's output in these formulas by the weight for each sample as other-mode product for the fairness of training generative model. By using this formula, we can focus on rarer samples compared to original strategy when we train the generative model. We use 4 datasets for evaluation in this work. Three datasets are used in original study of comfortGAN. These are labeled as dataset A, B, and C. In addition to the three datasets, we use our original dataset. It is labeled as dataset D. The number of samples, the number of features, and the number of classes are shown in this table. For the evaluation, we randomly choose 70% samples for training and the remaining 30% samples for the test. This is the architecture of comfortGAN's discriminator and generator. Generally, GANs is the framework which trains these networks alternately. We use the same architecture as the original comfortGAN in our work. The detailed description, such as the number of nodes and the kind of layers of each network, is shown in this figure. Please also refer our paper for more detail. Three metrics are used in comfortGAN and we use them in this work. The first one is variability of generated samples. It is defined as the difference between generated samples randomly drawn from the generated dataset. The second one is the diversity of generated samples with respect to the original dataset. It is defined as the difference between closest pairs from generated and original sample. It is calculated as Euclidean distance. The third one is machine learning accuracy using generated samples on classification. It is defined as the classification accuracy on the balanced mixture of generated and original samples. This is the result of the evaluation. We compare our method with three methods. The first one is baseline, which do not apply any data balancing. The second one is smooth. It is a predominant data augmentation. The third one is the original comfortGAN. As shown in the table, the diversity and accuracy were improved or the same compared to comfortGAN. Especially, the proposed method increased diversity for all datasets compared to original comfortGAN. However, the variability decreased in three datasets. This result shows that the weighted loss function works to generate different samples from the original dataset, while conserving the original trend. We conduct further evaluation to evaluate the similarity between the original dataset and balanced dataset. As shown in the figure, the proposed method has more similar distribution to the original dataset compared to comfortGAN. In addition, we compared the mean and median of air temperature among three datasets, such as the original dataset and the two balanced datasets. As shown in the table, the proposed method have smaller difference between the original dataset compared to comfortGAN. This result shows that the proposed method can generate air temperature data whose distribution is more similar to the original dataset than comfortGAN. This is the conclusion of a presentation. We propose a data balancing method for thermal comfort datasets using conditional Wasserstein GAN with a weighted loss function. The result shows the weighted loss function for GANs improves the diversity of the generated dataset. Our future work includes investigating how accuracy changes when the dataset's distribution and the number of samples are changed. Thank you.